In this video, we're going to cover the first few pages of the 6.7 handout on inner product spaces. We start out by defining what's called an inner product on a vector space. So if V is a vector space, could be any vector space, and Rn could be an abstract vector space, possibly. An inner product is a function that associates to each pair of vectors, u and v, in the vector space V, a real number denoted with this bracket notation. You can say bracket uv. I'm always going to read this as the inner product of u and v. And the inner product of u and v has to satisfy certain properties for all u, v, w in v and all real numbers or scalars c. So the first property is that the inner product of u in v equals the inner product of v in u. That's like a commutative property of inner product. Number two, the bracket of u, the inner product of u plus v and w is equal to the inner product of u and w plus the inner product of v and w. That's a distributive property. Number three, the inner product of a scalar times u in v is equal to that scalar times the inner product of u and v taken separately. And the way we should think of that is you can factor a scalar out in front of the inner product. And number four has two parts to it. The first part is the inner product of any vector with itself, that's the inner product of u with u, is always greater than or equal to 0. That means it can never be negative. And the second part of 4 says that if the inner product of a vector with itself is 0, then that vector has to be 0. And in fact, it's if and only if, meaning that's the only way it can happen, that there's no other vector whose inner product with itself is 0. So when you have a vector space with an inner product, we call that vector space an inner product space. So you kind of want to think analogously to dot product, even though it's not exactly the same as dot product. In fact, I wrote this little note here that we can talk about. You know, in chapter 1, we talked about Rn spaces. They're the most famous kind of vector space. In chapter 4, we introduced abstract vector spaces. We saw that there are other sets that can be considered to be a vector space, right? In the beginning of this chapter, in 6.1, we talked about dot product in Rn, and most of you are familiar with that dot product, I think. So that's kind of fits in with the Rn spaces from chapter 1. In 6.7 now, we're working analogously to dot product, but we're going to define this new inner product for abstract vector spaces. So what we're doing in 6.7, we think of as applying to our chapter 4 abstract vector spaces. But we're going to see that we also have alternative inner products that apply to the Rn's. So sometimes even Rn's have these inner products that are different from the standard dot product. Okay, let's continue on with the handout. Example 1, Rn with the inner product defined in 6.1, the dot product, is an inner product space. This is called the standard inner product in Rn. And I want to, so good old dot product is also an inner product, a special kind of inner product. I want to go back to the 6.1 handout, and actually I'm going to go to the second page of that 6.1 handout where we had something called Theorem 1. Those were properties of the inner product. Notice that there were A, B, C, D, 4 properties of the inner product that I think you probably thought, yeah, no big deal. They were not hard to think about. Notice that this abstract definition now of inner product in 6.7, there are these 4 properties that correspond exactly to the 4 properties of dot product that we talked about in 6.1. In 6.1, we were only talking about Rn spaces. In 6.7, we're allowing the possibility of other kinds of vector spaces, other kinds of dot product, you might say. And we have this new notation. All right, so we actually talked about example 1 in 6.1. Now let's move to example 2 here. In example 2, we're considering R3, so we're still working with one of the Rn's, and I'm saying U and V are vectors in R3. I'm writing them, the components horizontally to save a little bit of space. So the components of U are U1, U2, U3, of V are V1, V2, V3. And I'm defining this different kind of inner product, okay, for U and V. And I just made this up. I'm saying it's 2 times U1, V1 plus 3 times U2, V2 plus 4 times V3, U3, V3. It looks kind of like dot product, but we have these coefficients of 2, 3, and 4. You can think of those as weights. Sometimes this is called a weighted inner product on R3. And why I picked the weights 2, 3, and 4, I just picked three numbers there to use. And what I want you to see is that one can verify that the four properties are satisfied. And let's just go through and actually verify those 4 properties. I wrote this up ahead of time because this is not hard, but I do want you to see it. So here's our example that we're talking about here, example 2 in 6.7. We're in R3, so let U and V be vectors in R3. We're defining this weighted inner product. So this is the same inner product that I wrote on my 6.7 handout. And we're actually going to verify the 4 properties now, 1, 2, 3, and 4. So let's go down the line. Property 1, first of all, if the inner product of U and V is written as so, the inner product of V and U is just going to be 2 V1 U1 3 V2 U2 4 V3 U3. The positions of the V's and the U components are just reversed, right? But at this point we're just multiplying and adding numbers together here, right? So because I'm working with real numbers, of course I can interchange U1 V1 U2 V2 U3 V3. So it's not too hard to see that the inner product of V with U is equal to the inner product of U with V. That's what I have right here. So property 1 is verified. Property 2, I need a third vector to work with here. So I say let W be W1, W2, W3. Now we already know that if we add U and V together, we get what I've written here, right? A vector with those components. So now let's figure out what is the inner product of U plus V with W, and using my weird inner product I've just defined, well, that's 2 times the first component of the first vector, W1, plus 3 times the second component of the first vector, U plus V, times W2, plus 4 times the third component of that first vector, U plus V, times W3. And once I write this out, I can just apply basic algebra to it, distribute, rearrange terms, and it's because of what's going on with the basic algebra that when I write the 2U1, W1, 3U2, W2, 4U3, W3 term first, that's just the inner product of U and W. And then I have 3 other terms, 2V1, W1, 3V2, W2 plus 4V3, W3. That's just the inner product of V and W. So we've actually verified property 2. We've shown that this distributive property works. And now let's go on to the third property. And let C denote a scalar now. And I have to work with C times U, which is just C times each of the components of U, written that way. And so the inner product of CUV, if I apply my rule, is going to look like this: 2 CU1V1 plus 3 CU2V2 plus 4 CU3V3. And again, I can just, I don't need parentheses in there in that way. And I can actually factor out this real number C from each of those 3 terms using basic algebra. And so what I end up with is C times what's the expression for the inner product of u and v. So property 3 is verified here. Property 4. Property 4 is usually a little bit more subtle, and property 4 has two parts to it. The first part is if we take the inner product of a vector with itself. So according to this rule, I get 2u1u1 plus 3u2u2 plus 4u3u3. Of course, I can write that as 2u1 squared plus 3u2 squared plus 4u3 squared, right? And what you can notice here is there's no way this could ever be negative because of the squares and because of the coefficients here. The first term is always going to be greater than or equal to 0. Second term is greater than or equal to 0. Third term is greater than or equal to 0. That sum is always greater than or equal to 0. Okay, so we verified the first part of the fourth property. The second part of the fourth property is that issue about how the inner product of a vector with itself is 0 if and only if it's the 0 vector. So suppose that actually happens. Suppose the inner product of u with itself is 0. What does this actually mean? And here we kind of have to think about what's going on here. Again, because of the squares involved here, the only way the expression on the left can be 0 is if each one of these terms has to be equal to 0. And the only way each one of those terms can be equal to 0 is if u1 is equal to 0 and u2 is equal to 0 and u3 is equal to 0. If any one of them are non-zero, I'm going to get a sum here that is positive and not equal to 0. So you kind of have to think through the idea of it, but we've actually verified that the only way that the inner product of a vector with itself could be 0 is if that vector is 0. And so we verified the 4 properties for the example 2 situation. Now there's one comment here that folks have asked about too, down at the bottom. In parentheses, I say, by the way, do you notice that 2u1v1 plus 3u2v2 minus 4u3v3 is not an inner product? And can you see why? So it looks very similar to what I had in example 2. In fact, the only thing I changed here is I put in a minus sign for the third term. And it's really that minus sign that kills things. So let me just show you why, if it's not obvious to you, why that isn't an inner product. I mean, basically we would have to try to verify the properties again for this new expression, right? This new kind of inner product. And it turns out you actually can verify most of them, but where this breaks down is with property 4. And I guess I wrote this up separately too. So just referring to the parentheses at the bottom of page 1 on our 6.7 handout, this expression is not an inner product. And you know why? It's because property 4 is not satisfied. We can actually find a vector u such that the inner product of u with itself is negative. And that goes against property 4 that says when you take the inner product of any vector with itself, you always get a number that's greater than or equal to 0. So it's not too hard to make up an example that'll work here. So just notice that when I take the inner product of a vector with itself, using that rule, it still looks like I have all these squares, right? But because of the minus sign, I can actually subtract and get a negative. So here's an easy example. If I pick the vector 0, 0, 1, and plug it in and take the inner product of u with itself using this rule, I'm actually going to get 0 plus 0 minus 4, negative 4, which is not allowed. So just giving that counterexample there is enough to prove that my hypothetical inner product here really is not an inner product, does not work. So I'm going to stop this video here. I'm going to continue this in a second portion.